So welcome back. I'm Sucheta Kure from Nagoya University, who will be chairing this session. We have a lot of talks from Rutgers in this session. Right, so the first speaker will be Blakesley Burkhart. She'll be talking about supermassive black holes and how they, I guess, affect the IGM. So take it away.
Thank you. Yes, we have a little Rutgers takeover for the next 3 talks. I'm Blakesley Burkhart. I'm an assistant professor at Rutgers, and I'm also an associate research scientist at the Flatiron Institute, CCA. And today I will be talking about the intergalactic medium, in particular, the interesting things that we've been finding in the low redshift IGM and the puzzles that exist there. And we had an interesting discussion last week about where to find new physics. And there was a discussion about how all the new physics is going to be found at high redshift, because we can see everything at low redshift, like the observatories, the simulations, everything's good at low redshift, but the new physics is at high redshift. And actually, I'm going to show you a case of the exact opposite, where I feel like we really understand very well what's happening in the intergalactic medium from the Lyman-alpha forest from redshifts about 2 to 6. But everything below redshift of 1 is exciting and mysterious, and there's potentially interesting new physics. And really, my role here in this talk is to introduce Megan Tillman, who's the next speaker. And I also wanted to point out other students that have been working on this problem with me, Alex Gurvich at Northwestern, and then Megan Pericki, who's an undergrad at Rutgers. So a little outline of the talk. I'm going to give you all a little refresher about what is the Lyman-alpha forest, and also what it's been used for, especially at what I'm going to call high redshift, which isn't always high redshift for everyone, but this is like redshift of around 1.6 or so to 6. There's been really just an amazing, over the last several decades, insightful research, both in the intergalactic medium, the physics, the temperature, the state of the UV ionizing field in intergalactic space, but also in precision cosmology. And it's something that I think it's good to think about how that's so successful there. And that really motivates like why the low redshift Lyman-alpha forest and IGM is mysterious. Why doesn't it match our cosmological simulations? Why is it problematic to measure the UVB there? Is there new physics there? And then I'll show you that some of that tension in the low redshift forest between simulations and observations gets alleviated by the inclusion of AGN feedback, but of course feedback is always messy. So there's still a lot of questions there as well. So what is the Lyman-alpha forest? So if you have a background quasar and you have line of sight moving towards us in space through the intergalactic medium, that light will be absorbed by the neutral hydrogen between us and the background source. And that absorption produces this beautiful array of absorption lines from the Lyman-alpha line here, all the way down through the other Lyman series, Lyman beta, Lyman gamma, and so on. And this produces what we call the Lyman-alpha forest and also the forest of the other Lyman lines. And using absorption line spectroscopy, we can take these lines and look at their fluxes. We can measure their optical depths. We can then measure their column densities, their widths, etc., and do physics based on those absorption lines. And so that's what's been done at a range of redshifts. So here I'm showing you 2 spectra towards background quasars at different redshifts. So redshift of 0.158. In order to get into that low redshift regime, you're essentially in the close to the rest frame UV, which necessitates space-based observatories. So this you need a UV space telescope like FUSE or like COS or like GALEX. And that's why, in part, the low redshift forest has been more challenging, right? You have to go space. You have to build a space telescope. At higher redshifts, the Lyman-alpha line gets redshifted into optical. So then you can do all your fun science on the Lyman-alpha forest from the ground. And you also can see, this is an example quasar from redshift 3.6. The forest here, these absorption lines are much thicker, right? So this thickening of the forest indicates higher cosmic density and higher optical depths. And here's a little cartoon of just these quasars moving through the, and the lines of sight going through the IGM. You only get a partial picture from these skewers of the full IGM. So what insights do we gain from this? Well, first of all, because we see these absorption lines, right, and we can measure the optical depths, and the optical depths are low, we know that the IGM must be highly ionized, at least up to around redshift of 6 or so. Where does this ionizing flux come from? It comes from quasars, it comes from star-forming galaxies, quasars mostly in the kind of later redshifts, like redshifts less than 2, and the star-forming galaxies at the higher redshifts. We can also probe with the Lyman-alpha forest as we push to the higher and higher redshifts, where the forest becomes essentially optically thick, the end of the epoch of reionization, right? And so this has been done with the so-called Gunn-Peterson test, and the spectra from quasars around redshift of 6 or so show this trough formation where the forest just dies out completely, and the optical depth becomes greater than we could see any transmitted flux here. So this is one of the classical signatures now of the end of reionization. And in one of our probes of that, classical like redshift of 6 is the end of reionization, is really coming from primarily the Lyman-alpha forest measurements. All right, what about IGM physics, right? Not just reionization and cosmology, but where do we get things like the temperature of the IGM, the state of the ionizing photons? Where does all that interesting science come into play? And it comes into play that at redshifts, less than 6, so like 4 on downwards, the Lyman-alpha forest is probably in pretty good photoionization equilibrium. The mean free path of the UV photons is longer than the individual sources, so the UV background is more or less kind of constant everywhere, so you don't have to worry about individual sources too much. And then you can use photoionization equilibrium here to relate the intensity of the photoionization rate with the densities of hydrogen, and also, of course, the recombination of hydrogen through the temperature-dependent recombination coefficient. Then you can analytically compute what your expected optical depth will be. Why am I telling you this? Because it's super powerful, right? So given this prediction for the optical depth, given the measured optical depths, one can then estimate things like the photoionization rate, so the UV background, the temperature of the IGM, the baryonic overdensity, which then you can relate to the dark matter density. So there's just so much rich science you can do with this very simple ionization equilibrium picture. Okay, and I'll get back to this gamma here, this photoionization rate, in a second. So what are the successes of this picture? All right, so one is, as I've said, this estimation of gamma, the photoionization rate of neutral hydrogen. And the literature on this is really vast. So this is just one summary plot from redshift of 6, where we kind of stop being able to see the Lyman-alpha forest, all the way down to redshift of 0. And the way people do these calculations of gamma is very simply, they say, okay, we have this photoionization equilibrium. We can relate the column density distribution, that's this dn dx here, to directly to the optical depth. Once we have the optical depth, all we need is some consensus, some counting of the number of ionizing photons for hydrogen, right? So we need some emissivity estimation. But once we have those two things, we can plug them in and estimate directly the photoionization rate of hydrogen. This is super important, right? Especially at high redshift, where the UV flux can kind of put a minimum mass on the mass of dwarf galaxies. It can affect the amount of hydrogen in the IGM, et cetera. So this estimation of gamma is very important. What else is a success here of the kind of higher redshift Lyman-alpha forest? Well, a lot of us here in the room are simulators and theorists, and we love our cosmological hydrodynamic simulations, and we love lambda CDM. And if we put lambda CDM together with an estimation of that photoionization rate, that gamma, we can reproduce all of the Lyman-alpha forest observations at redshifts greater than 2. Right? So it's just dark matter plus gamma, and assuming that the neutral hydrogen is going to follow the dark matter, and that the photoionization rate will set the amount of hydrogen, voila, we get the Lyman-alpha forest, right? And to show you how right we get it, it's amazing. So this is a column density distribution. This plot will come up again and again. So on the x-axis here, column density and the number of absorbers from Alate et al. 2011. The points here with the little error bars are Lyman-alpha forest measurements at a range of redshifts with different optical ground-based instrumentation. So you can see that they curve like very nicely, and you get some different power laws and different regimes. And what I want to point out here is that this red line, which is one of the mini cosmological hydro simulations that gets this right, is not a fit. This red line is not a fit to this data. This is just what comes out of the hydrodynamic simulation. So this is a huge success, right? All we're putting in here is photoionization equilibrium, a gamma, and dark matter from lambda CDM. And this picture of the balancing photoheating and photoionization in the intergalactic medium seems to work very, very well at these redshifts. What else works? I'm not going to spend more time talking about what else works with the high redshift forest, but just to point out a few things which are really fascinating studies. So one can study warm dark matter to cold dark matter paradigms with the Lyman-alpha forest and place limits on warm or cold dark matter models. There's been a lot of studies looking at how to relate the flux power spectrum from the Lyman-alpha forest to the dark matter power spectrum, and also to place limits on cosmological parameters like omega baryon or sigma 8. And then you can even do BAO science with the Lyman-alpha forest. And there's many studies that measure the acoustic peak from the Lyman-alpha forest. So there's all this precision cosmology, and there's a whole community of precision cosmology with the Lyman-alpha forest. So tons and tons of successes. So why am I sitting up here telling you there's a mystery now, right? What is this mystery at low redshift? Well, first of all, where's Sultan? Why should we care about low redshift? Yeah. Why should we care about low redshift? All the new physics at high redshift. Well, not in this case. So, and actually at the low redshift, one reason why we should care is, especially at the low redshift, most of the baryons in the IGM are in the IGM. They're not in galaxies. They're not in these collapsed luminous objects. So this is, if we care about baryons and we want to know what they're doing, we got to look in the IGM. And we got to look at low redshift in the UV. This is challenging, right? Space-based telescopes are expensive. It is really hard to convince NASA to give you, many hundreds of millions of dollars to build a UV instrument. Ask me about that, I know. So, we have a couple now that have been looking at low redshift background quasars for a couple decades now. So GALEX, FUSE, COS. There was a really important landmark study by Danforth et al. 2016 that basically categorized and collected all the samples from COS and FUSE and GALEX into a category of these low redshift absorbers, especially the COS data being very sensitive compared to FUSE and GALEX. So really, it wasn't until about 2016 that there was enough statistics to really start to do this Lyman-alpha forest, statistical studies like we've had at the high redshift. And then, of course, the simulators, shout out to you guys, baryonic physics is hard, right? We all know AGN feedback, supernova feedback, how you treat that. It's all in a subgrid, star formation, right? So this becomes also hard from the simulator side as well. And there was a very important paper by Juna Kohlmeier in 2014 that was one of the first to report, whoa, there is a problem here. The low redshift forest, so, a classical statistic like the column density distribution, does not match our cosmological simulations, right? And so Juna had looked at a gadget simulation that at the time, was pretty state-of-the-art, included star formation feedback, et cetera. And also included a standard, at the time, the most kind of state-of-the-art UVB model from Hart and Maddow 12. So for the gamma here, and the gadget simulation with the Hart and Maddow 12 photoionization rate here is in black, and the data, the COS data here is in the magenta, right? And so this paper pointed out that in order to match the actual COS data, you need to add an additional 5 times more ionizing photons than Hart and Maddow 12. where do those photons come from? Because the budget from quasars is very well known. The budget from galaxies may be a little less well known because, you know, maybe the escape fractions, like the photons, maybe are leaking out a little more or a little less. So that's a parameter you can tune. But a factor of 5 is a lot. So where is that factor of 5 coming from? Right? And so just to give you a visualization of what a factor of 5 increase in, you know, ionizing photons will look like. This is also from Juna's paper, right? So this is the kind of original Hart-Maddow 12. So this is what the structure of neutral hydrogen in the IgM would look like. You know, and if you turn on the light bulb a lot more, you ionize more hydrogen. So there's overall less hydrogen available, right? This will look significantly different in terms of the amount of hydrogen. So this is kind of akin to, like, you know, if you increase gamma here, right, you're going to decrease the amount of neutral hydrogen. This is like burning the forest, like you're like torching it with UV photons. All right, so there were a lot of initial ideas what could be going on. Some of them may be more conventional, like, oh, well, we just don't know the escape fractions very well. Or maybe there's some extra heating terms, like from cosmic rays, you know, like the usual things we like to like throw out there, like magnetic fields, like we don't know what's going on. Some more exotic things like photons, you know, like from dark matter decay, like, and there's even been some more recent papers about this, which are still, I think, very interesting thoughts, or some combination of all of these ideas, right? And like the most like attractive thing to appeal to would be to update the UVB models, right? Just like, oh, we need to like tune up the escape fractions a little bit. And that's what people have mostly done. They've kind of updated their emissivity calculations. But doing that doesn't get you all the way to the factor of 5, right? At most, it gets you about halfway there. So it can't be the full solution to matching the Lyman-alpha forest at low redshift. And I got really excited about this, you know, after I, you know, talked with Juna and saw her give a talk on this in 2016. And then I had a really, really smart undergrad REU student working with me at the time, Alex Gurvich, who, you know, I was like, let's just look at Illustris and like, let's just see what Illustris, the Lyman-alpha forest at low redshift looks like. And lo and behold, we found that, you know, very far from a perfect match here, but definitely significantly different than the gadget simulations in the black here. So the green line here is the Illustris, and then the magenta lines here are the Danforth 16 observations. So like what is altering the forest here so significantly? You know, it's still lambda CDM, right? You know, you can account here for the UVB, so you know what that's doing. So like it's still not matching it once you account for all those kind of classical Lyman-alpha paradigm things, like what's going on. And this was Alex's study in 2017, and we really dug deeply into this. We looked at, of course, the UVB, resolution, hydrodynamics. Is it star formation? Is it AGN feedback? And the UVB actually is certainly, again, is not the answer. So here's our little test where we change the Illustris UVB. So the original Illustris simulations, also TNG, they use the Fauché-Giguère 09 photoionization rate, the UVB background model. So that's the green line here. And then the black line is, you know, switching it up to Hart-Maddow. Hart-Maddow is a little less ionizing than Fauché-Giguère. So you do get a shift there, but it's not enough, again, to explain the gadget simulations. Like, why are they so much off? They're over-predicting the amount of neutral gas. Why is that? We looked at stellar feedback. Stellar feedback actually seems to do almost nothing in Illustris, at least, compared, you know, changing, you know, either turning off the stellar feedback, you know, boosting it, or looking at the fiducial model. That's those dotted lines here. You know, once you get to the higher column densities, like into the damped Lyman-alpha systems, there starts to be maybe some difference, but at the lower column densities where, you know, the classical Lyman-alpha forest is, there's not really any difference at all. And I already have given you the answer in the title of my talk, right? So I'll just get right to it. AGN feedback seems to be a critical component of this story at the low redshift. And here's a little visualization from Illustris with AGN feedback. This is the neutral hydrogen column density. So you're directly looking at the Lyman-alpha forest here. You know, it's dramatic between a simulation with AGN feedback and without AGN feedback. And again, in a similar way that the photoionization rate alters the forest, right? If you increase it, it's essentially removing neutral gas. Temperature increases will do a similar thing, although you need more temperature because the recombination coefficient scales more weakly with temperature. But nevertheless, if you have a bunch of temperature shifts in the forest, that will shift your column density distribution. And I'm almost out of time, so I'll introduce Megan's talk, and she'll take it further from here. Is really how AGN are doing this work. So since the 2017 study, we've been looking at changing the UVB, changing the AGN models. TNG and Illustris, they're a nice test case because they use the same UVB model, the same gamma, but they've totally reworked the feedback model. So, keeping the UVB the same and like propagating that to simulation, you can see the difference between the black and red lines are pretty dramatic, and neither of them actually matches Danforth 16, right? So oopsies. Still not getting the forest right, but that's okay. Like, we're learning a lot, right? So you can visually see, this is at low redshift, the difference between Illustris and Illustris TNG in terms of the column density and also the temperature, right? So Illustris having this really aggressive AGN feedback model, the gas is very hot. It strongly affects the forest, whereas TNG is a little more mild. The temperature is less dramatic. All of these things are showing up in the Lyman-alpha forest. The Lyman-alpha forest is sensitive to this. The other thing I'll mention is that this effect is not the temperature effect of the AGN. We don't see it at high redshift, right? So at redshift 2, this is Illustris and Illustris TNG. They look very similar, right? And this is really, this effect of the AGN on heating the forest is really happening at low redshift. And I think I'm almost done here. Yeah, I'll just end on this movie. This was the starting movie of the talk. This is actually the SIMBA model. And I'll start the movie over. At redshift of 5 is when the black hole feedback starts to turn on. The black holes have grown to a size where they can introduce this jet mode feedback. And the forest statistics, right, they're kind of global skewers that are moving through the forest. This effect doesn't propagate in a statistical sense until about redshift of 1 or so. But from redshift of 1 onward, this heating from the AGN becomes volume filling. And so this is where, from redshift 1 on downward is probably going to be the most critical redshift range to look at the forest in this way. There's still mysteries. The B distribution, we can talk about that more later. This doesn't match at all with observations. And I'll throw up my conclusions here. In particular, right? So the good news and the bad news. Good news, we can calibrate AGN feedback models on the low redshift forest. Bad news here is that UVB models that are measured from the low redshift forest are in danger. It may not be without a good AGN feedback model calibrated, it might be difficult to do that. Yeah, I'll stop there.
So we have some time for questions. Okay. First the name and then yeah.
Yeah, thanks for the great talk. So my name is Haowen Zhang. So my question is, well, maybe it's going to be covered in the next talk, but so do you know, like at low redshift, what are because we know that in TNG there are multiple different modes for AGN feedback. Do you know what is the dominant AGN feedback mode that's contributing to like when you're changing from, say, Illustris to TNG, what's the dominant feedback mode that's causing this difference?
Yeah, so I'll let Megan give you like a fuller answer, but from Illustris to TNG, the bubble mode in Illustris is really the like aggressive heating mode. And TNG like totally reworked that to like a kinetic mode, which is less, it's not blowing out these extremely hot bubbles. And so that's the main difference between TNG and Illustris that really altered the results for the forest. And then the SIMBA mode, as you can see, is actually totally different as well. So Megan's going to talk about that.
Hi, yeah, Christian Jesperson, Princeton. So thanks for this really cool talk with some fantastic visualizations. So one thing that I noticed, I just want to hear if that's a coincidence or if there's something to it, is that when you show the plot with the difference between illustrious and TNG, they seem to match the observations well in different regimes. Mm-hmm. Like at the low column density, illustrious is pretty good, and the high column density TNG is pretty good. Is that a coincidence, or is there actually something physical in that?
There is something physical there, and I think it's the question really actually is what sets the slope. And the slope is something we're still thinking about. The slope changes when you change the AGN feedback model. And it's unclear exactly why different feedback modes are changing particular ranges of the column density. You can imagine like a more aggressive AGN feedback mode, but it's not heating, it's just moving gas around, might affect more the halos and not so much the diffuse gas, so it'll affect the higher column densities rather than the lower column densities. So that could be part of it. This slope, though, is really interesting and key because the amplitude of the column density distribution can be shifted around by playing with the UVB, right, the gamma. But the only way to really alter the slope seems to be moving the gas around in some way, which the feedback is doing.
Thank you. Josh Beek here. So we've seen a big shift, or a possible big shift, in circumgalactic medium studies when including cosmic rays. Mm-hmm. And in particular, the sense of that, I think, is that it enables there to be more dense, cool material. So you can do things like accounting for magnesium 2 absorbers and other weird things that are sort of surprising. I guess I'm wondering if that same sense would tend to flatten the slope. If we include cosmics, because you just throw more of the kitchen sink in, it'll obviously solve your problem.
I think that's something we definitely want to look at, because cosmic rays potentially could alter the column density distribution through ionization. They're another ionizing source other than the photons, but they're also a heating source. And I didn't quite get to it, but one clear remaining discrepancy with the observations is the absorption line widths. So the non-thermal widths are way too broad. Cosmic rays could be broadening things. That's certainly one option. But even including AGN feedback, we're not able to explain. The simulations are way too narrow. The observations are way too broad. Whatever. Yeah, they're definitely mismatched in terms of the B distribution. So yeah.
So yeah, we'll have Peter and then afterwards.
I'm Peter Brucey. Thanks for a great talk, Blakesley. I just had a question about whether you've looked at the correlation functions, like either autocorrelation of the lines or a cross correlation between the Lyman-alpha forest and galaxies, and whether that could help with answering the question, is it AGN feedback versus UVB or something else?
That's an interesting idea. We've looked at the Lyman-alpha forest power spectrum. The power spectrum is sensitive to all of this. We haven't done any cross correlations with the galaxies. So that could be something interesting to look at, to see which active AGN, exactly how they're messing with the forest. I think that could be cool. Yeah.
Mark Huertas Company here. Thank you very much for the talk. I had somehow a naive question, but I was thinking, so the AGN modeling in the recipe, let's say in hydrosims, is calibrated more or less to reproduce stellar properties of galaxies, like sizes and this kind of stuff. And so why there are no constraints on these? Is that because there's a tension, or they cannot reconcile having sizes properly and the properties of the AGM, or it's just because it's ignored? I just wanted to know.
No one has calibrated an AGN feedback model on the Lyman-alpha forest yet. So it's all based on galaxy properties,
but
right?
Is it because there's a tension, or we cannot reconcile both, or it's just because ignorance? Okay.
Yeah, it's ripe for the picking. Someone should definitely do it, and I mean we've been talking about doing it. So if anyone has interest in that, let's chat.
Chris Lovell. This might be another question that maybe gets answered in the next talk, but in Simba, I think Sultan showed in a paper a couple of years ago that even at Redshift 3, the CDDF is under-predicted in the Simba model. And this may be due to this very, energetic feedback that doesn't really touch the galaxies. It just kind of heats up these big bubbles.
Right.
What was my question? It's gone now. Oh, maybe it was a comment.
Is that a problem?
No, yeah.
Yeah.
No, I said, okay. The question was, is this conclusion that everything is, everything's good at high redshift? Is that really the case? And even with these extreme feedback models, is there still some tension at the high redshifts? And maybe that's a regime where we can learn more about the physics, where it's a little bit cleaner, perhaps.
Yeah, I mean, I haven't looked at SIMBA at Z of 3. I think any Cosmos simulation that can't reproduce the forest at those redshifts, needs to reevaluate whatever the feedback model or whatever is causing that. Because essentially all of them get the high redshift forest correct. So yeah, I haven't seen that result from SIMBA.
All right, we'll have to move on. Sorry about that. So let's thank the speaker again.